Now we want to build up an understanding the whole model, namely the two reactants in sequence together with the feedback function.
Okay, so should we try and find the steady state first?
Steady state. How is the steady state defined?
When the rates don't change anymore, when the rate equations are both equal to 0.
It's the balanced state where the sum of all the contributions to the rate are 0, so they all balance each out nicely, the positive and the negative contributions. And we reach a homeostatic or a steady state, something that is predictably then also measurable, because it's a robust state that is stable against fluctuations.
Okay, so we can do this in two ways. Should we do this using fsolve first? So the function fsolve.
Algebraically, fsolve would be the way to do it.
Okay, so we need to first define a function that represents our differential equations in completeness. So we've only got part here, so we've only got the inhibition. We actually need a function that's going to be both parts. So let's just call this f for simplicity. So it's going to be an anonymous function again, so it starts with an at, brackets with our variables inside. And now it's going to take x. Now x is going to be a two-element matrix, so a row vector in this case. So we're expecting output to be of 2 elements as well. So the first element is of this form, so the feedback inhibition function minus the value of x1. We've already defined our feedback inhibition function, but let's use the one that's parameterized here, shall we?
We might use the parameters to find the outcome under these specific rate constants that go into the model here.
Well, we always need specific rate constants. Well, for doing it this way, we'll need the specific rate constants for finding the steady state. Okay, so we need to give it an input. So we know it takes x, and if we recall, our value of x here was equivalent to our value of x2 here. So it will take the second element in x, big X, sorry. And of course minus x1. And then our second equation is easier, it's just x1 minus x2. So x1 minus x2.
Capital, then it's nice and consistent. And so one thing that we should mention, that in this attempt to make it as simple as possible, we have of course made some rather artificial assumptions, namely that the second, third and the fourth term in this model don't have an actual rate constant written there explicitly, or in other terms, rate constants are all assumed to be equal to 1.
Yes.
This is not, of course, a generic case for the biological system. They would be different, but we just keep things tidy here, and it will make a quantitative change if the rate constants are different from 1, and you will have to write them in.
The behavior would be the same, though. It would just be different numbers that you would get at.
Qualitatively, the outcome will be the same, but quantitatively, numbers will be different that you get from simulations. Yes?
So okay, let's solve this. So I said before we just need to use the fsolve function. So let's say the steady state is equal to fsolve. Give it the function f, and we need to give it some values. Gil, could you remind me what these values? They're x0, so they're the initial guesses. The initial guesses at what these solutions would be?
Initial guesses are arbitrary in this case because we haven't really looked at it in detail to make educated guesses. So I think a good way to start with would to not put these equal to 0. Take something that's a finite value, so for example 1, but we must say it's arbitrary in this moment. We don't have any hints of how to choose these values, but I'm sure we'll be fine here. There might be more complicated cases in more complicated models where it's actually important to have a good guess.
Yes, we'll come to that again in a minute.
Yeah.
Of course, we need 2 guesses because we've got an x1 and x2.
Each reactant will have a concentration assumed. In this case, we start with 1, but it can be other numbers as well. And for practical purposes, it's good to check with different numbers if you suspect that the outcome may be more complicated than what we have here.
Okay, shall we see what happens?
What have you done? You have run this section here, and you get the information from MATLAB that equation is solved. So that's probably output from the fsolve function.
Quite happy with the output equation solved. It looks quite positive.
And all the text says there's no problem, for short. And stopping criteria means that this is a numerical way of arriving at these values that are then plotted at the end. So it means you could actually give your criteria for the precision with which you want to have this. And we're not going to go into the detail of this, it's a Newton iteration, but we want to just say that you can have a little bit more details if you want to be very precise in this. However, we are very happy with the outcome. We have here in the command window steady state equal to and then two numerical values. How do we interpret these values? What are they supposed to mean?
So when x1 is equal to about 2.7 and x2 is equal to about 2.7 as well, then it will just be a straight line if we plot it.
Aha. So that means the two values represent our two variables, and we have to interpret the numbers as concentrations. So say millimole per liter or millimole per microliter, whatever you define. It's then dependent on your definition. And we see the first number is related to the first variable, or what we call x1, the first reactant, and the second number corresponds to the value for the second variable. Okay?
Okay, that's good.
I think we're happy for this, and it's of course not the fact that they are both identical here has to do with the simplifications that we have made and setting rate constants equal to 1.
If we can actually see that from our second equation, so we're trying to solve the case when x1 minus x2 is equal to 0, and obviously that is equal to when x1 is equal to x2.
When they are the same, right. So looking at the second equation, when they are both the same, then they will be solved already. So we know they must be equal, but then the first equation gives them the actual numerical value. So that's our algebraic treatment, and steady state predictions would be if you have set up an experiment with continuous supply of nutrients, say cells under cell culture conditions, and you wait for a certain time until everything has had opportunity to settle down and find its steady state, then this is the value that's predicted by the model that you're supposed to measure if you look at concentrations.
Okay, so there's another way we can find the steady state.
Just 1 second.
Sure.
Can we take a look at the steady state under other conditions?
Of course.
Say, what if the feedback inhibition is quadratic rather than linear in x2?
If you recall, we'd already defined a function under that case, so feedback inhibition 2, where n is 2. So we'll just substitute that in there and run this section. Okay, and we get a different answer.
So what do we get? We get a different answer. Still, both values are the same, but we get a number that is smaller than the previous one.
Yeah.
So that tells us something that we could have predicted already from looking at the inhibition function, that in this case, the steady state for these concentrations larger than 1 is actually stronger inhibited by the feedback because we have a quadratic inhibition, and the value larger than 1 makes it stronger impact and less steady state concentration for both variables in this case. Okay, let's look at the second way of finding the same answer.
Okay, so that's to find the steady state symbolically.
This is an important strategy to learn the distinction between the two ways to operate in MATLAB. And we hear from the feedback that people typically have more problem with understanding the symbolic manipulation of such expressions as these functions. So we might just do this exercise here.
Okay. So of course, the first thing we need to do is to define to MATLAB some symbolic variables. We're going to call these x1 and x2 with small x's just to be different from the values we gave it previously.
So we get the idea that this is a different way of talking about the same variables. Okay, our symbolic way.
We next need to define the symbolic functions. So f1 is equal to, well, let's put the values of the constants in now. So a was 1 over 0.1 plus another 0.1 times by x2.
That's our nonlinear feedback.
And then minus x1.
That finishes the first equation.
And f2 is just x1 minus x2.
So we have a symbolic way of writing the same model, and now we can work with it.
Okay, so we can solve that using the solve function. So we need to set up our equation. So our equation is it's two-dimensional. So we have f1, f2. They're both equal to 0, so we can just do that as a shorthand.
Right. This means that we want to find out under which conditions these two equations are simultaneously equal to 0, which incidentally is our definition of the steady state.
Just going to clear our output on the left so we can see what's happening, and then I'll run this section. Okay, it's taking a little bit of time. Okay, so it says answer equals x1 2 by 1 sim and x2 2 by 1 sim.
Right, that's rather cryptic.
Okay, so we didn't happen to know what that means. That means that we've got two row vectors coming out of the output of this function. So actually we need to capture both of those independently. So we need a two-dimensional row vector with x1 steady state and x2 steady state, say, as our variable names. And I can put a semicolon on the end because we don't want the output from that other ones. Okay.
Right, so we assign this to an output that we can then later deal with.
So let's capture that by running this. Okay, let's check. Okay, yeah, so I did get output properly. So x1.
So what do we get? x1, x2.
So that's x1 steady state. Is this rather complicated number? And x2 steady state. Well, these two numbers rather than these two numbers for x2 steady state.
That looks incredibly incomprehensible.
Yeah.
What can we do with this? So how do we have to interpret this? That's an important thing to learn, that this is actually meaningful output, but we need to understand it. So first of all, why is there two numbers in each of these vectors?
Well, maybe we have two solutions.
Aha, it means that MATLAB has actually found two solutions. And you can see there's now a difference compared to the algebraic before. We have found a solution before, but now this symbolic manipulation tells us that this set of equations actually has two possible solutions. And how do we now get those numbers correct? What does it mean, minus 41 to the power of something?
Well, we can use the eval function. But I think it's important to point out here that x1 steady state is giving the steady state values of x1 at the first steady state and the second. x2 steady state is giving the steady state values of x2 at the first and the second steady states. So actually when we're looking at a steady state, we want the top value and the top value. And for a second steady state, it's the bottom value and the bottom value.
Yes, so the top values together will be our solution for the first steady state, and the bottom values taken together will be our solution for the second steady state. Do you think you can print those values for us somehow? It might be so much easier. Evaluate.
So we need to use the evaluate function. We can passitate another array. Again, we need to make sure we're getting them in the right order. So actually we want x1 steady state 1 and x2 steady state 1. It's the first steady state.
That would be the first one. And
let's just copy and paste this to get steady state 2 and just change these subscripts to 2 and 2. So the first element, or the steady state 1 first element, steady state 1 second element, and steady state 2 first element, second element.
Right. Right, so that's an important thing, and it's good to practice this a little bit, maybe with another function, and to get used to it, how to actually extract the steady state. So x1 doesn't capture a steady state, it's only the steady state values for two steady states of the first variable. Okay, that looks good to me.
Okay,
And I'd be curious to see the values, although one of the steady states we know already.
Okay. So this is the value for steady state 1, and this is the value for steady state 2. So this is the one we saw before, right?
Right,
2.7-ish.
2.7 is what we saw before. Both numbers are equal.
We have both numbers equal for the other one, but they're negative.
They're negative, meaning
Well, it's not realistic. You can't have negative concentrations.
there's not much point in further looking at this in detail. And now we can also understand why we didn't see that one in our first algebraic solution. We would have found this probably if we had started with negative initial concentrations for both reactants. So here's the way. There are two steady states just mathematically from a point of view of the mathematical solution, but in terms of the biological interpretation, of course, it's this steady state with positive real numbers, the 2.7 that we are interested in, and we can ignore this negative number there. Right, and of course, if you would run the same thing with the quadratic term,
Okay, let's see what happens.
is that easy to do?
Well, we just need to put a quadratic term in our symbolic functions.
Take x2 to the power of 2.
Okay, let's try running this. Whoa! Well, we get our first solution 2 and 2, that's fine.
Yes, 2
That's
and
the one
2
we
is
did
what we
expect.
expected. So we have a positive, well-defined steady state where both concentrations are equal. Plus
this imaginary complex number.
So not only is the other steady state negative, so not realistic in biological terms, it's not even a rational number anymore. It's complex numbers. So for those who like complex numbers, please look at the second steady state. For us biologically oriented people, we want to ignore that one as well.
And actually, we have a third steady state in this case, which is the corresponding other imaginary number. Just out of interest, just because we had 2 before, but actually...
Because complex numbers always come in pairs, that makes things even more complicated. So I think it's very good news for us that we don't need to consider this in the moment. And as you can see, you get a similar output, but of course, if you have it symbolically, there's further manipulations that you can do. You could say take the derivative and find slopes at different points of the function, if you were interested in that.